So,
okay. So I'm Colin Slater. I'm currently the Deputy Associate Director for System Performance at Rubin Observatory. I've been doing data management things on the observatory for a long time now. Alex started with a bit of where did he get his start, and so I thought I would do the same. So I got my start working on telescopes on this nice 24-inch telescope, where when I first went in and said I'd like to work on astronomy, the guy I talked to said, "Oh, great! I need somebody. We're going to replace the rollers on the dome with roller skate wheels because it's going to help out prevent leaks." And I thought, this is not what I thought I was signing up for when I said I was interested in astronomy. But I didn't really have much of a choice at the time, so I said, "Sure, let's do it." And ended up climbing all over this machine and learning so much here that would end up being relevant to this machine. In between, I worked on pan-stars. That's how I got my start in sort of large survey astronomy. And then today, what a nice machine. Okay, so a bit of outline. So Alex started talking about detectors and sort of all the chain of things that go wrong as you go from photons to numbers in the computer. And everything that the pipelines do is basically working that in the opposite direction, saying, okay, how do I undo all these things that were that resulted from this instrumental effect, this detector effect, that instrumental effect. And so I'm kind of going to walk backwards through this process. The initial stages is what we call instrumental signature removal. We're removing all the things that are purely an artifact of the detector or purely an artifact of the telescope or the optics. I think if we get to it, we're going to go into background subtraction, which is not strictly speaking part of instrumental signature removal, but it's sort of the next stage along the process that we're going to walk back. And so that will sort of lead into what we're talking about tomorrow morning. And also I'll say, please interrupt me with questions. So there's going so many tangents, I love going on tangents, so happy to do so. Okay, let's go straight into instrumental signature removal. Our goal here really is to output an image that tells us about the relative brightness of things on the sky for everything sometimes like we're just trying to undo all the variations that are caused by effects that aren't actually related to physical flux through the sky. And that means that we're not going to necessarily think about absolute calibration here. Our goal isn't to say, okay, this one pixel has 10 counts and that means exactly this many nanojancies coming from the sky. We just want to get all the pixels onto the same basis so that in later stages of the pipeline, we'll come through and measure actual stars and galaxies. And those will be what we use for converting counts into nanojancies. ISR, we're just going to get the pixel effect. We're just going to fix the effects that all the pixels are on the same basis so that the catalog can actually make sense when we go to downstream processing. So broadly speaking, this is super broad, but it's just a useful framework for thinking about this, that we have both additive effects in the images and multiplicative effects in the images. So sometimes something has been added, sort of irrespective of any amount of flux coming from the sky. Yeah, we'll get into examples of that. And then in many cases, we have something where some amount of the flux from the sky is basically taken away. It's eaten, it's put somewhere that we can't actually measure it, but that's always a fraction of the incoming signal. And so that correction is going to be a rescaling of the image rather than just an adding and subtraction. There are exceptions. There are things that sort of span both of these categories a little bit. And like the worst of all is that there are really nonlinear effects that are really undesirable. But those nonlinear effects are, for the most part, small. And so we're not going to really talk about them there's some things that we're just not going to deal with at all. If we have bad columns are they're permanently bad. There's no information in there. I can't rescale anything to get that column to be correct again. So we're just going to mask it and not try and let it mess up our measurements. So this diagram is really the signal chain for Rubin's camera. Started to think about some of this in the previous session, but here's where, like, when we're talking about correcting all these factors, we really do need to know exactly where in the process they occur, because that tells us sort of we have to do all the corrections in the right order, otherwise it will get sort of non-physical answers. So over here in the actual detector, we talked about parallel transfer and serial transfer. There's some effects that just literally happen in the silicon. The cosmic ray in the silicon is in the silicon. This is the schematic for the readout and the amplifier that's on the chip itself. There's some cabling, talked about crosstalk before. That's one of the sources of crosstalk. There's a preamp, integration, bias injection, and the ADC. This is sort of all the parts that ISR is kind of most concerned about. Like, do we understand the gains that are being put on the signal from both of these devices here? Bias injection, we'll talk more about bias in a second. And the analog to digital conversion itself has potentially some interesting effects going on. And then at the end, we come out with our pixel counts. So okay, so we talked, looked at raw images. We haven't looked at bias images yet. But part of this sort of, Alex briefly mentioned is that between integrating the signal from the pixel and actually reading it out and converting it to a digital value, we inject bias, right? And this is a voltage that's designed to keep the measurement off of the zero floor, because the ADC doesn't want to deal with negative values. It doesn't want to deal with values that are too close to zero. And so we always want to keep our measurements in the range the ADC is happy to deal with. And so we add this constant voltage to every single pixel before we get to the analog to digital conversion. But this is fraught. Like, nothing in analog electronics is ever constant. And we are measuring very, very small signals here, and so very small variations in this bias actually matters. And we should keep in mind that, like, this would all be easier if we were reading out like 1 pixel per second. That's really easy to get a precise measurement. We're not doing that though. We're trying to read out 400,000 pixels per second. LSST-CAM reads out in about 2 to 3 seconds, the entire camera. There's a lot of data, there's a lot of clocking going on. And so basically there's so many sort of voltages that are need to be varying quickly in order to move pixels through the readout process. But that means that this nice constant voltage that we want to be adding really can't be constant. It's affected by all of these other effects going on in the camera. So you can almost see, you don't sort of see that there's, oh, sorry, I should say, that bias, we think of it as an image, right? We're going to create a bias image which reflects like what we think that value that we added to the pixel was, but it's really a time-dependent thing. So in the process of reading out the image, we're sending pixels through the readout chain one by one in a time order, in a fixed order every single time we read out the image. And so the assertion, the hope is that if there are variations in the bias levels, that at least is constant in this like, that it's the same every single time we read out the image, right? So if I read out the image, there might be some variation that happens in the bias at the very start of a column, at the very start of a row, but at least it's going to be the same way every single time I do that. So we can make a bias image that's that reflects this any of these effects. Yeah, sorry, it's not just like a random thing that happens every single time afresh, every single time we read an image. We see that we're seeing the same change in the bias as a function of time in the readout, which is the same as position in the image every single time we read up the camera. So we're really looking for repeatability. For the most part, the camera is extremely repeatable. When it's not repeatable, that's like that. That's when we have a really hard time. We have to start doing sort of kind of out there methods for correcting things. I was just going to mention dark current because it's sort of one of the classical things we talk about I mean, for years and years, dark current was a problem in CCDs, and it's basically not a problem anymore. This is basically in the early days, basically defects in the silicon itself, which sort of let charge leak into the pixels over time. It's sort of like a hot pixel, but very, very small level, and in fact, a sort of uniform effect across the entire sensor. This is no longer an issue, but it's sort of useful for thinking about ways in which actual defects in the silicon affect the image itself. So we basically don't need to correct for this anymore, but we do just to be safe. It adds in LSST-cam, it adds less than 1/100th of a count per second, so not that significant anymore. But it was really one of the dominant issues a lot earlier. It's also why we one of the main reasons for cooling CCDs, so reduce the dark current. Okay. Multiplicative corrections are sort of kind of a bigger category. So we sort of think of a lot of things as being some multiplicative factor on the light coming into the sensor. So I have, so let's say, okay, I'm just going to say, okay, I'm going to define that by default, I'm going to say the light coming into the detector is a factor of 1.0. If there's a speck of dust that's blocking some amount of light, if it's letting only 95% of the light through on that particular area of the sensor, I'm going to make a flat field image that has 0.95 in those affected pixels. And that's going to let me say that if I take the measured image, I divide by this flat field image, it brings that measurement back up to the level that I would have had if I hadn't had this dust in the way, or this gunk on the sensor, or a smudge on the lens, or all sorts of sort of optical effects that you can think of. And this is what we're going to look at later. We're going to actually look at flats in the hands-on section. So I'm going to skip doing the tour of all the things that we see in the flat field. So let's go straight to how do we even measure this? So ideally, you would just have some perfectly uniform thing in the sky that we can measure, but we don't have that. So what else can we measure? How can I try and measure the uniform, the response function of all these pixels? Thoughts, ideas? Yes.
An illuminated sheet inside the dome.
A big bench, right?
Yes.
Okay. What's the advantage of this?
You don't have to open the dome.
You don't have to open the dome. Great. Exactly right. What's the disadvantage of this?
It has wrinkles.
It's full of wrinkles. You didn't iron it first. There are other ideas. There are other ways to measure this. Opening the, oh, sorry.
Oh. If you do open the dome, then maybe looking at the sun, or maybe looking at the moon.
let's go to the moon. Even it is. I know people who have lit parts of the dome on fire by leaving the telescope open. And that was a very small telescope. Rubin, just for fun, Rubin, we cannot get within probably 10, 20 degrees of the moon. It actually, the amount of charge going into the pixels to like receive that brightness actually gets the power supply, like the power supplies get kind of mad about that amount of current and they trip offline. And the camera team has to come and reset everything and they like look sternly at us. What do you do? I don't know. I didn't hear the suggestion about looking at the sun. We can't look at the moon. We can't, like, we just can't. Also, the moon is super lumpy. You can look near the moon because that's sort of right, but it's not very uniform actually. Like, it's a really steep function wave. Yeah.
Jumbotron, just giant TV.
Is that better than the bed sheet?
Iron my TV.
So I will either do that area of the sky where the illumination more or less like constant, or I will look at the dome.
Where in the sky is the illumination constant?
Kind of like sunset.
Sunset, twilight. Okay, you're right. It is like twilight is very uniform. What's the downside of observing at twilight? Anyone else? Yeah.
Might not be able to open the dome.
Why not?
Weather.
Usually weather's okay. It's mostly just waiting for the sun to go down. It's true that if the dome is going to fail to cooperate with us, it's going to be at the start of the night. And this is legitimately a problem with twilight flax, is that it's actually very hard to get the entire observatory running in time before twilight's gone. Yeah.
The sun goes down really fast.
The sun goes down really fast. So you're trying to take twilight flats, and everyone in the observing room is like freaking out, like, we got to get on the sky, we get on the sky now, and somebody's fixing something that's broken, and like somebody's not pointing the right place, and it's
When you take a flight, your counts are low and you're like crap.
right. You're chasing this illumination pattern, which is constantly getting fainter and fainter and fainter, and so you have to increase your exposure time, and this is a scary game, which like everyone gets kind of freaked out about. Yeah.
So how bright is the twilight sky compared to the moon? Does the camera team get mad?
Camera team will not get mad at us for observing twilight generally. Yeah.
If there's a cloud, those be
We observe on a cloud. It's an interesting thought. I'd have to think about that a little bit more. You need like a cloud that's backlit by the moon, but I don't know if it's too lumpy or not. These are fun, yeah.
You have to think of my mind. Like, for example, if you do like the twilight, maybe affected by the cerebral light, for example, like for gradients in
Is it affected by zodiacal light? Zodiacal light is very faint. I don't think okay, I'll inject one other idea here, which is that you can make flats just by pointing at the sky, right? You try and point someplace that does not have very many stars, and you take a lot of those images and do a lot of masking and a lot of interpolating, and you can get a flat that way. It's a lot of work, but I don't point out the ecliptic so you don't get into the zodiacal light. I think. these are all fun. We should probably keep rolling. So these are some real twilight flats. The biggest, okay, I said earlier that like twilight flats, the hard part is that like it makes everyone really nervous and anxious, and it's difficult to get it in before the sun goes down, goes too far down. Really the biggest problem is that when you have an 8-meter telescope, you see stars all the time. And so these are all stars, and they don't leak in the twilight flats, and it's kind of a pain. So yeah, we can, an 8-meter telescope to see stars through a ton of clouds. It's amazing. Okay, so what Rubin is basically centered on is that we just have the big bed sheet here. I don't know the actual weight of this bed sheet. It probably weighs, it feels like it must weigh 2 tons. It is enormous. I cannot convey like standing in front of it. It is this big, and it is also like right in front of the telescope. You can see that. See, someone forgot to iron out this and this and this and this and this. So there are irregularities that are still in the flat field screen. You can actually see that here. So this is, we have a system that shines LEDs directly onto the flat field screen. It's actually coming out of here, the telescope's over here, and it reflects back. And you can just see by eye the variations in that. Like you can see these cool rings. Cool to look at, kind of not really nice for data reduction. So we have to do basically a lot of tricks to try and even that out. This is just a cool shot of all the different colors we can illuminate the flat field screen with. So we need to flat field every single filter individually, and we have a set of LEDs, typically 1 or 2 different colors for each filter. That illuminates that flat field screen to get as much light through that particular filter. So like U-band, like you really need UV LEDs to illuminate, to get enough flux on the flat field screen to measure the flat field. And U-band, you really need IR LEDs are easy to come by, but you really need something totally different at the red end to get enough flux to go through wideband. So calibration team spends a ton of time arguing for us to spend time taking all these calibration images for them, all these in-dome flat field screens, and then processing those into flat field images. So we're basically relying on lots of averaging in order to make those uniform. We're relying on this assertion that any non-uniformities in the camera, which is what we're trying to measure, aren't going to be precisely matched by non-uniformities in the calibration screen itself. And so by moving these around, you can at least try and average out rather than compounding the problem. Oh, sorry.
In the last slide.
Yeah.
Just because kind of looks like the darker. Or is these what she's not to say?
You mean fainter?
Yeah.
Or do you mean physically smaller?
And then the extendedness of.
This was just somebody with a cell phone in the dome taking this picture. It's meant to be as similar of coverage as possible. We're not relying on these being the same brightness, right? We're just trying to get uniformity, and then we will come back and measure. We will do calibration once we've measured sources and stars on the sky. We just want uniformity. Yes.
How often do you do blast work?
If it was up to the calibration team, it would be every single day. We don't have enough time to do that. So typically, if we have to close for weather, they'll spend all night doing these calibrations. And if we are open, then they won't get any of this because we'll go on sky immediately.
Can you do it during the day?
The dome is not light tight enough for this, right? Like it's like mostly light tight, but the sun is bright, and so like a tiny amount of sunlight getting into this makes it so now you have some weird pattern that's on your top of the screen. Great questions. I love it. Okay. So right, so we're hoping that at least any deficiencies differ enough that we can average them out. We're relying on different effects having different spatial scales. So like it seemed like there was some kind of gradient, like the edges of the flat field screen really aren't quite as bright as they should be. This is a challenge. It means that the calibration folks have to go in and fit functions to those outer parts of that. And that's sort of contentious, and they have to spend a lot of time doing that. So it's not like ideally it would be perfect, but in fact we do have to do some fitting techniques. And this is also hard at the edge of the focal plane because the telescope itself has vignetting, where not all like if you're looking straight on, if you're like the thing that you're pointing the telescope directly at, all of those photons get to the detector. But on the edge of the field of view, some of those photons actually are obstructed by different features in the telescope, but they don't actually all make it to the camera. And so you start to lose sensitivity off to the side, which is kind of what we're trying to measure with this anyways. But that means that there's a lot of challenges out there. Questions here before I take a historical interlude? Yeah.
So this question is a little further back when you were talking about dark curtains. But they're not related to dark curtains.
Yeah.
It's just when you did mention that you cool the CCDs. So when you cool the CCDs with silicon as a semiconductor, do you encounter any kind of conduction issues that because do you have like any kind of electromagnetic effects that kind of start showing up at lower temperatures? That
to my knowledge, look at Alex.
So to eliminate the quantum efficiency, and the red end does change.
Yeah.
And it's temperature dependent. You don't want to cool them down too much where the chargeability decreases and you can't charge. Both of those are temperature dependent. The reduction in the recourse tends to be more beneficial. As long as you calibrate the temperature that you're operating at stable, then your result.
what are the temperatures that you can keep the CCD at?
Oh, I should know that off the top of my head. It's like minus 120 C, something like that. There was a mistake the other week where we ran for a few days at the wrong temperature, and that was like 10 degrees off, and that made the calibration team mad. Everything we do wrong makes the calibration team mad. Because it changes the quantum efficiency, Cal was saying. Okay, so historical interlude, and Alex already showed one of these pictures, but this I just think is interesting because it this changed how I think about a lot of this. So when we talk about flats, I was talking about like stuff like dust, junk on the lenses, stuff like that, stuff that like removes light from the light path. And we're saying, okay, if I remove 5% of the light, then I divide by this number 0.95, and that brings me back up to what a uniform sensitivity, or what I would have seen if I had a uniform sensitivity. We're all like in the early 2000s, we're just constantly thinking about sensitivity variations in terms of as what we're doing with flat fielding. And And then DECCAM came along, and I'm not going to talk about the tape bumps here, but these rings, this is a flat field image. This is looking at a uniform, is probably the calibration screen. But there are these rings here, and they look like sensitivity variations, and in some ways they are, but they are not. Quantum efficiency variations. I would say quantum efficiency, they're just like what we think of as like the effectiveness of silicon in converting photons into electrons. So this was weird, and fortunately the DECCAM folks figured this out. They plotted the positions of stars they measured repeatedly. So if I measure the same star a whole bunch of times, I know where it is in the sky, and I can ask, well, each time I see that star at a given point on this chip, does it seem to scatter this way relative to the mean position, or that way relative to the mean position? And if I plot those measurements in pixel coordinates, you would see that in this region of the sensor, the positions of the stars seem to scatter away from the rings, this ring, and this ring, and this ring, and this ring. And that's not a sensitivity effect. This is the boundaries of the pixels being shifted. It's the same, it's similar to what we were talking about earlier in the brighter, fatter effect, where the boundaries change a little bit because of charge, but this was actually baked into the sensors. And the reason why this is sort of fascinating is that this is making the pixels bigger, not making them more sensitive. And so if I do the naive flat fielding, I will actually do the exact wrong thing. I will make the problem worse. And that just like blew my mind when I first heard about this. I think the way to think about it is like, okay, here's a cut through a star, and okay, let's say there's 100 counts in the star. I'm going to measure 100 photons. In the central pixel, I got most of those photons. Let's say I measure 80, and in the wings I measure 20, right? Okay, fine. But if I, for whatever reason, if this pixel is bigger, now I've collected more counts into that pixel. It's like eaten some of the counts that should have previously gone to its neighbors, right? So that's fine, I can deal with that. But the flat field tells me, sorry, just to do some quick math here. The flat field tells me that I want to divide by a number greater than 1. I want to say, the flat field would say, this pixel, it's too sensitive. Its counts are over-representing what should actually be measured here. And so when I do the division, it's going to correct this in the wrong direction. I'm going to actually measure the wrong flexibility star. This is sort of hard to wrap your head around exactly why this is going on, but making the pixel size variation is just not correctable in the same way that pixel sensitivity variations are corrected. Okay, and if I should have inserted a better transition slide here. This is something. But okay, what do I want to say there? Just to wrap up, so like, there's more complicated things. Like today in the year 2025, we know that flat fields are actually more complicated. It's not just we're measuring sensitivity variations, we're dividing. We know there's area variations going on as well. We know there's tree rings. We know there's basically these are all sort of electrostatic features. The tape bumps that we saw in DECCAM. Because DECCAM saw this first, there was time to work with the CCD vendors to minimize these effects in the LSST-CAM sensors. So LSST-CAM does see very, very faint tree rings, but they're much reduced compared to what they were in DECCAM. So in practice, like this is not actually messing up our flat fields. Like the tree rings are not messing up our flat fields. But it's a thing that we have to like keep in mind of like what actually is the physical cause of the effect that we're trying to correct. So okay, I put this image here just to say that those were the instrumental signature effect ISR steps that I was going to talk about, and these are the ISR steps that I could talk about, and we are just going to have to skip many of them because they're all a lot of them are sort of along similar lines or mostly about like sort of thinking carefully what's affecting the camera and how to correct for it. Is there any one of these that stands out that you think you really want to know more about? Behind first and then ahead. Oh yeah. This is what I was saying, where bad pixels, can't do anything about it. Just gonna mask them. Yes, they are applied sequentially, which is why making this diagram was a big fight about what's the right order to do this in, because it matters. Like it really, you have to mimic the order that these effects are like created in the signal chain and do it in reverse. Otherwise, you'll get weird issues. So like that was this diagram was a success just because it got us to write down the correct order. I think behind you were first.
Okay, so I have a question. So why does we do the order of serial overscan in and parallel overscan? I think maybe
That's a great question. I have no idea.
I think probably what makes more sense to me is to do the serial and parallel overscan first and then okay.
We don't want to do parallel overscan ever if we could get away with it.
Oh.
That's really something for dealing with misbehaving chips. Ideally, we won't do that at all. I mean, most chips we won't have to. At the moment, it's there just in case. But I honestly don't know why it's not over here.
What's dithering digitized counts?
There's a number of effects which are like because they're like intrinsic to the way the analog to digital converter has to output binary values. I remember this off the top of my head. There's some weird effects that makes. I'm not going to guess. I will just tell you the wrong thing, so I can't explain that one. Yeah.
So the steps where you do combined residual 2D bias and bias subtraction.
Yeah.
So that is, I guess, you're using a deconvolution algorithm or some kind of algorithm in order to subtract the residuals from the image.
No, that's just straight making a bias image, which is just what we measure if we read out nothing.
Okay.
We take 0-second images,
Okay.
make an image, average a bunch of those, and then subtract it.
Okay, so no 2D
convolution.
Gaussians or anything.
Exactly.
Okay.
No, tree rings are like baked into the silicon physically. Like decam, they've been there forever, they'll be there forever. Same with LSST.
Can you go back to the previous slide? Why? So my understanding was that in the third row, we would divide 5 by 1.1 because then we. Yeah, can you still?
Yeah, you're right. I didn't do that 1.0 right. Yeah. Right. These should be below 0. These should be below 1. And so it won't be 5 here, it'll be like 6 or 7 or something. And so that'll make this not quite as bad. Yeah, because this is why I should like look at my math more carefully. Okay. I have a few more minutes and I just wanted to sort of go to the next step beyond ISR because we needed to get to the next stages in the pipeline that we're going to talk about later. And that's really sky background. This is not ISR. So we separated this in the pipelines, but I'm just going to talk about it because it's important. And it's possibly the hardest problem. So just to state it pretty simply, so okay, have my source here. I've drawn a line through it and I've shown the counts. This is a raw image. This is the raw counts coming off of that per pixel. And so I have both a bias, and that's something that the camera inserts. The camera says, I'm giving you these volts in every single pixel. We have light coming from the star, right? But we also have background, which is light coming from the sky. And this is not the same as bias. These are two totally different things that we need to treat differently. We cannot do any photometry until we've done background subtraction. Like if I add up the light in this set of pixels here, if I include all of the tan colored stuff, that's not light from the star, so I'm going to get the wrong answer. I need to only measure the light from the star, not the tan, not the blue. So we have to do background subtraction. This is sort of, it's a subtraction, so it's kind of the same as bias, but it's not like the same physics at all. Bias is something the camera does. It's repeatable every time. The spatial structure is in pixel coordinates. Background is coming from the Earth, coming from the atmosphere. It's not fixed in time in any way, and it might have actual astrophysical light involved as well. I've already talked about zodiacal light. That's a form of background. This is always just fun to sort of think a little bit more about what even is this. It turns out that in the very upper atmosphere, 100-kilometer altitudes, all of these atoms that we think about as when we're talking about spectroscopy of stars and nebula and whatever, those actually are emitting light also in the atmosphere. So sodium D line is one of the brightest sources. This is an old paper, so these are Johnson bands, not Hughes bands, but B sort of I-ish. So we have bright sodium lines, oxygen lines. OH is making these sort of low vibrational bands. All of this light is sort of the dominant thing that we're seeing in our images. It's this bulk here. There's a lot of it. And so as 20 magnitudes per square arc second is a rough number to hold in your mind. So that's like brighter than the structures that we're actually trying to observe. So, okay, it's meant for two reasons. One is that we need to subtract it. That's going to be a challenge, but let's set that aside for a moment. The other is just that this is what contributes to the noise in our star, in the stars that we're measuring. So when we're talking about measuring, say, okay, we have Poisson noise, we're counting electrons. The noise in my measurement of the electrons in this pixel is the square root of n. What is n? Is it this? Is it this? It's the unfortunate one. It's all the light coming from the background as well that is involved in this square root of n noise. And so that is why we talk about our images being background limited, because our faint sources, the noise in those sources is dominated by the background light. So this is basically why darker sites are better. Space is really dark. It's really great. Oh, here we're back to the moon. This is why we don't try to observe close to the moon, in addition to the fact that the camera team will get mad. yeah, so all of these background sources are just going to sort of increase the amount of noise before we on our measurement. And then even once we've dealt with that, we have some extra noise, but now we need to actually subtract off this background. Well, here's my favorite galaxy. Galaxies are a smooth ramping light distribution. How am I going to be able to measure the background level against a smooth ramping light distribution? So what you can actually see here is there's kind of like a bright ring around this galaxy. This is where background subtraction has actually gone wrong. And so it's measured a little bit of light from the galaxy as the background, and then it subtracted that, leaving this divot around the galaxy. And this is just generally an incredibly hard problem, and there's no like good solution to this. There's just compromises. And so we've spent a lot of work lately trying to make it so that we're not creating divots around every single galaxy, every single bright big galaxy. This basically comes down to an iterative process. So I need to sort of fit some kind of smooth function here. That means I need to mask out all of these stars. I probably need to mask out the center of this galaxy. But here's where the trade-offs come in. If I mask out too much, then I don't know where I should estimate the background. If I don't mask out enough of it, then I'm going to estimate part of the galaxy's light as background light. And it's just hard. It's hard, but it's necessary. Those were all the slides I have. So we have time for questions. Thoughts? Questions? Fusion. Apprehensions.
Might be something I missed out, but in your background subtraction, you also have to make ionospheric corrections, like for example, for spectroscopy, I guess.
Do spectroscopists do that?
I mean, for us in the radio, for like, especially for our higher frequencies, in order to do spectral line synthesis, I guess we have to do ionospheric correction. So I was wondering if that's something that affects your frequencies as well.
No, we are not worried about the free electron count in the atmosphere. And I should know why optical bands don't care about that, but I can't remember off the top of my head. Those bands do vary mostly because of the sun, actually. They get excited by UV emission from the sun, and so depending on where we are in the solar cycle, those lights might get brighter or fainter. Kind of fun physics. Other fusion topics of wonder. Yes. None of this. ISR is the cheapest part of the processing because, yeah, more or less. So we're going to talk about later is measurement. So actually taking a star or a galaxy and trying to basically fit functions to it to measure its size and brightness. That is all more complicated. And Wednesday or Thursday, we're talking about warping images to make coeds, also way more expensive. Just doing all the ISR steps is really the cheapest part of the pipeline. Yes.
You might have said this already, but how does LSST do the background subtraction right now?
It's a complicated set of trade-offs. Yes, I do not know all the details of what they're doing there. There's a few experts in background subtraction that spend all their time thinking about it. That's-
We have time for one more question.
There's a bunch of chat. Someone else is watching the chat.
So in the overscan examples we've been looking at, there's some kind of number that's associated with the background, how for each amplifier on a CCD, the background level is different. But that's not related to bias, right? The fact that there's variations in each amplifier and there's a different number when you check the overscan, that's not related to bias.
Overscan is measuring bias.
It is.
It is.
But we don't use it for bias correction. We make a bias image instead.
We do both actually.
So how did, okay,
So that's why that diagram is so winding and convoluted, is because we do both subtract what we measure for the overscan region, and then the bias image that we subtract is actually just a correction to that. But you could do only one, or you could do only the other, and it would still work, but
Okay.
For complicated reasons, they do both. Cool. We're fine.
Let's leave it there and thank Colin again. As always, if there's some part of the break, not looking at a screen. Okay, screen,